Hey, Networking 101 sure does beat sitting in the principal's office. You know, when it comes to just starting out networking, probably to me, one of the more complex topics to understand was QoS. And there's a lot of reasons behind that. You know, I mean, it's using some very legacy terminology and even technology to support some of our newer services out there. Before we get into drawing a single slide or I go through anything on here, here's the most important thing that you can remember about QoS. QoS is only as good as the weakest link. To get it to work correctly, you've got to carry it through your network end to end. If there's a place that's not marked, that packet, that frame is going to be dropped on your network. If you don't remember anything else on here, just remember as you're setting this up, if your network is not working correctly, if you're not getting the results, find out where QoS is not, and that's probably where the problem actually exists on here. All right, so what is QoS? Well, first off, we got to break this down. QoS is just multiple forms, right? You got MPLS EXP, you've got, layer 2, 3, got even down to layer 1 where you can prioritize port traffic and stuff. Realistically, the stuff that we deal with on a day-to-day basis, QoS comes down to two different methods. There's a layer 2 method and there's a layer 3 method. The layer 2 method is really pretty simple, really. It's basically you just take a standard Ethernet frame, which has an MTU size of 1518, and you add what's called a tag on the end of it. That'll actually stretch this frame out. It'll go from 1518 to 1522. It'll actually grow in size. Some of the older school switches, when you'd actually do this on here, they would start giving you these errors, these odd errors like baby giant errors, and you'd be looking in the log, baby giant, what the heck is this, But it would see this as a bigger frame, and so it'd give you these really odd errors. But what this tag does is that it allows you, it sets 3 new fields on here. One of them is what's called a CFI, a conical frame indicator, and that was really for backward compatibility for Ethernet or token ring. So unless you got a bunch of MAG cards on your network, this will never ever be changed. This will always be Ethernet. The other field is actually what we're calling our QoS field. This is 802.1p is the standard that governs that. And what that does is that it's split out and it gives us 3 extra bits on here to actually start prioritizing our traffic. 000 to 111. And if you add this up real quick, you'll notice that you've got a priority from 0 to 7. And so on a 802.1p or a layer 2 type of QoS, what we notice is that we've got 7 different QoS priorities that we can set up. Now the other frame on here is probably one you're more familiar with. This is 802.1q. This is the VLAN field. This gives us 12 different fields, or 2 to the 12th, which takes you down to about 4,096. So you'll know that when you're setting up your VLANs, your choice is in here between 0 and 4,095. For your VLANs. There are a couple reserved ones in here too. We're not going to get into that stuff. But that's really how the layer 2 stuff works. Now, the most important thing to remember about this is that for this to work correctly, let me go to another cleaner slide, is that I've got to be able, my devices have to end to end be able to pass that tag down. So when I'm sending down that bigger frame on this network, it's my little tag here. These are my switches. I'm going to notice that my traffic QoS is really concerned about this upstream device. I'm not concerned about the downstream because that device, that packet has already flowed through here. I've tagged it, I've classified it in here so it actually flows out. And this next stream, when it gets that packet, the first thing it does is it pops that tag off of it. It'll just pop that booger right off, just like a dandelion, and it'll handle the traffic. And then if its egress rules are that it applies another tag to it, that switch will then re-tag that frame, send it on down to the next switch. And the same thing will happen over and over and over again. This is a very layer 2 centric type of QoS, obviously. And it works great for like phones. That's why like when you're setting up your phones, you have a voice VLAN. We set up that voice VLAN so that we can not only segregate our voice traffic, but so we get the option to actually allow that QoS tag to be on there. And that's where that really comes in. That tag, that QoS piece, allows me to prioritize that voice traffic. Because remember, voice is very small, but it's incredibly time sensitive on that network, right? I mean, you're looking about 150 milliseconds to transfer that data across. Now, works great, right? But what if I've got a router? What if I got to send that past a layer 3 boundary? How do I actually set that piece of it up? Well, This is where it gets a little bit complex. This is where folks kind of stumble a bit. It certainly is where I did when I first started messing around with this stuff. What you're looking at here is basically you're tagging inside the frame. Back in, I believe it's RFC 792, what you're looking at is the IETF actually specified that you have a QoS or a field in here that they actually termed IPP or IP precedence. And that gives you the option to have QoS fields from 1 to, or from 0 to 7. Sounds pretty familiar, right? And it worked pretty good. And that will work pretty darn good on land because my options are a lot smaller and that stuff. But once I start routing this in the wild and start having a bunch of different options, I'm really more concerned not necessarily about a voice flow or a video flow. I'm concerned about flows and grouping them together, especially at the service provider level. You know, I'm aggregating all this traffic in, and I want to set up different types of services on here. I want to be able to apply different classes to the flows that come in. Layer 3 traffic, or diff serve, what we call differentiated services, is where this came into. We actually extended this out, and it gave us 64 different options or different binary equivalents to actually set or apply these classes to. We call this, like I said, differentiated services, or as all the cool kids call it, diff serve. And diff serve is broken out. These 64 pieces are what you call diff serve code points, or DSCPs, is how they're referred to. Now, these code points don't necessarily prioritize that packet itself, but it's designed to actually aggregate a flow of traffic. And so it puts it in a certain class to make sure. It's just like sitting on the bus at school, right? All the cool kids sit in the back, all the goobers sit in the front, you know, and you just kind of picked where you sit. This is what we're looking at, is how we're classifying that traffic on this network. Now, it looks a little complex when you start looking at this stuff, and when, you know, a lot of folks see this, you know, it's like, oh my goodness, this is really complex. It's really not. Just kind of keep a couple things straight. Number one is that we've got a couple different classes here. We have our class selector 6, and we have our expedited forwarding. Expedited forwarding is the absolute highest class of traffic that you can apply in a diff serve code point. That is usually DFCP 46, and anytime the network sees that, it knows to put it in the priority queue. There's two pieces of QoS that you really have to take into account, whether it's layer 2 or layer 3. It's also the queuing aspect of it. How does the switch interpret that data as it's going through here? We'll get to that in just a second. But this is the most important piece, is keeping this stuff straight. As you see, this is what we have as recommended type priorities on the network. And you'll see that, you know, we've made some changes here that, because, you know, we're setting up broadcast video. That's a pretty cool effect, huh? I wish I knew how to do that. I stole this slide off of somebody. But what we did is we're broadcasting our video a little bit higher now than what we used to, you know, with our call signaling stuff, because we're noticing a real increase in how greedy that is and how we want to make sure that that traffic is so bursty. It gets out a whole bunch of stuff, especially if there's a lot of movement, right? HD and stuff, it's only going to send the stuff that moves. It's going to try and keep that background static. But every time there's a movement, like in my hands here and stuff, that increases how much bandwidth that thing is using. So my QoS becomes very important, because now it's going to slow down. You're not seeing much movement on the screen. And that's where this really gets to be very, very, very critical. So now we know how, or see at least how these diff serve code points can match up. Another thing I want to draw your eye to real quick is that below everything you have what's called a scavenger queue, or a scavenger, where we can say stuff is below best effort. Best effort is typically what Ethernet generally is. If you say that anything's running at default, default is best effort. You can actually downgrade stuff and just say, well, it's not that important, right? Like your TPS reports or something. Let's go ahead and just, you know, downgrade that stuff. You can put that in scavenger data, which means that it gets the lowest priority of everything on the network, even the stuff that's not even classified. Now, how does this work? Well, this is where a lot of people get a little stuck on this, because at Cisco, we classify our switches by this obscure looking odd group of numbers and letters, right? Here's the secret to decoding this. 1P3Q3T really equates to this. 1P means this switch has one priority queue, right? So that means I've got one queue that all my priority traffic, whether it's the layer 2, priority 7, or it's diff serve code point 46, it's going to go in that one queue, and that's the priority queue. It's going to have all the meat and taters, and that's where stuff's going to be serviced. We have 3 other configurable queues that we can configure up with 3 different drop thresholds. So that means that in a normal switch, this is a 4Q switch here, like you'll see on a standard stackable. That's why I wanted to use this in here. So a standard stackable, you're going to see you got 4 Qs, and you're actually allocating resources based upon how much Q you have or how much Q depth that you have as your packets are flowing into these queues or in these slots. That's how that information is going to be handled, how it's going to be serviced, or how it's going to be processed inside of that switch. Every switch is going to have its own little quirk about how it transfers that traffic. Some switches will say that unless the traffic gets 80% congested, it's not going to mess with any QoS. Other switches are going to say, we always use QoS. It goes into a scheduler, and based upon how it's hitting that queue, we're going to go ahead and forward that traffic out. So if something hits a priority queue, then it gets serviced at first, and we empty that queue out before we do everything else. That's called a starvation queue, and it's typically not recommended because for the obvious reasons you can see. Then you have a scheduler queue where it actually goes out and it looks at how much traffic I have. It's going to say, okay, I'm going to let 10% of priority, 5% of other queues, and it's going to kind of work those drop thresholds, which is why this number is important, because that becomes very critical in how you configure this up and stuff. And that's all up to you. Now, we do have default settings, of course, that you can take, but you can actually set this up and configure it. The bigger the switch, like a 6500, you're going to see a lot more stuff. You're going to see like it'll have 1 priority queue. It'll probably have, maybe 8, well, probably not 8, but 7 other queues with 7 different drop thresholds, right? Your bigger switches are going to give you a lot more options to set that up because they've got a lot bigger queue depth. That's all memory. And it's not only the memory itself, but it's also the CPU that allows it to schedule and go in there and grab that data and process it. And that's really what QoS is all about, right? It's allowing me to take all these diff-serve code points and all those layer 2 stuff and be able to map them to a certain queue and allow me to configure that stuff up on how I want that traffic to flow. I can classify, I can determine what's important on my network, and really have my switch have the intelligence to set this up. But remember, no matter how this stuff works, we certainly have to know it for exams and certification, all that stuff. But the most important thing to take away from all this stuff here is QoS is only as strong as the weakest link on the network. If there's one device that doesn't support it, or a device that's older out there and it's in the way, and it's got a slower or shallower queue depth and stuff on here, that's going to be the weak point or the problem on your network. Keep an eye on that, because I've had many times go out and troubleshoot stuff and things should be working right. Sure enough, there's a switch that wasn't even documented that doesn't support this, and then that was the holdup of the whole network.